Hello students and welcome back to Study Room. So if you remember in the last video, I said that we are going to study spherical mirrors next. So today the topic that we will be covering is spherical mirrors. So what exactly is a spherical mirror? Let's first read from the PPT and then I'll explain it to you. So it says that the reflecting surface of curved mirrors can be considered as the part of the surface of a sphere. Such mirrors, whose reflecting surfaces are spherical, are known as spherical mirrors. Now, what does this mean? This means, as I told you at the end of the last video, but I will recap it here, is suppose that this is a sphere. You all know what a sphere is. Obviously, you've seen a ball. Now, suppose that this sphere is actually a mirror on the outside. Like if you have seen a cricket ball, just think that the outer surface of the cricket ball is like a mirror. So, which side would I shade on? Would I shade on this side or would I shade on this side? Think about it. Which side am I going to shade on? I have said that the outer surface of the cricket ball, suppose this is a cricket ball, the outer surface I have said is a mirror. So, which part of the mirror do we shade? The reflecting or the non-reflecting surface? Yes, we shade the non-reflecting surface of the mirror. Now, if the outer surface is the mirror surface, then where would we shade? Yes, we would shade on the inner part. So, consider that this is a mirror. Okay, this is a mirror. I am shading the inner part to show you that this is a mirror from the outside. Now, if I cut out this bit, what am I going to get? If I cut this out, I am going to get a mirror like this, right? Inner part shaded, right? This mirror is like bulging outwards. Can you see this? The shape of this mirror. Compare it with the plain mirror that you have in your house. It's like a simple rectangle. But this has this bulging out shape. Similarly, if I have a sphere, suppose the same cricket ball that we considered, but the inner surface of the cricket ball, you can't see a cricket ball's inner surface, right? Think about that inner surface is the reflecting surface. So where would we shade this time? Yes, we would shade on the outer surface like this. Okay. Now, if I want to see the mirror and it's in the form of a cricket ball, I can't see the inner surface. What would I do? Again, I cut it like this. I cut it like this. So what do I get? I get this mirror. But this time what is different is it is shaded like this on the outside, right? Because the inner part here is the reflecting surface. So can you see this mirror is going inside? This mirror is bulging outside and this mirror is almost as if it's being pushed inside, right? They're both in the shape of a crescent moon, like so to say. Have you seen a moon, a crescent moon like this? They're both in the shape of this, but just the difference is that which part is the reflecting surface. Okay? Moving on. So you've understood this, that spherical mirrors are a part of a sphere. They are shaped, they're basically mirrors whose reflecting surfaces are spherical. Okay, those are known as spherical mirrors. Now, what are the types of spherical mirrors? I also covered this in the last part of the video, but I would do it again. Now, there are two types of mirrors as it is given here. One is concave mirror and the other is convex mirror. Now, the first mirror that I drew just in the last PPT that I said that its reflecting surface is bulging out. If I am saying the reflecting surface is bulging out, so I'll shade this part. So you see this surface is like, it's almost as if it's coming out. Like when you get hurt, something hits you on the head or you hit your head somewhere, your head like bulges out like this, right? That's the shape of the mirror. It's like bulging out. Imagine this is that after you get hit, this is that bulge. Okay, so this is how you can remember that this bulging out part is the convex mirror, the one that bulges out. The mirror that is pushed inside, almost as if like when you hit something soft, like if you have a small wall of clay and you hit it with your hand or you push it with your hand, it would go inside, right? It would cave inside in that shape, right? So this is how you can remember it. A mirror that is, have you seen a cave? You've seen caves, right? You've seen caves in movies, in mountains. You've probably seen it in real life also. So how is a cave? Is a cave coming out, or is a cave like going into the mountain? Is the cave inside the mountain, right? It's not coming out, right? So this part, can you see now I'm talking about this here? I'm talking about this part. Can you see this part is caving inside, right? So this is the non-reflecting surface, and this is where you will stand if you're looking into a concave mirror. This is where you will stand. In case of a convex mirror, this is where you will stand, because this part is the non-reflecting surface. So if you're standing behind a mirror, you won't be able to see your reflection. If you're standing here behind the mirror on the non-reflecting part, you won't be able to see your reflection. You will only be able to see your reflection if you are standing towards the reflecting part. Okay, so now you won't forget this. The mirror in which the reflecting surface is caving in, like this one, is a concave mirror. The reflecting surface in which the spherical mirror in which the reflecting surface is bulging out, like you've been hit on the head, is a convex mirror. Okay, these are the two types of mirrors that you have to study about. Okay, now we are going to do some important terms related to spherical mirrors. So the terms are: 1 is aperture, 2 pole, 3 is center of curvature, 4 is the radius of curvature, and 5 is the focal length. Now I am going to use just one figure to explain all of this to you. Okay. Now I am going to do this in case of a concave mirror which is caving inside. Now you can draw it in case of a convex mirror for your practice. Okay. Now I'll be drawing a concave mirror like this. Can you see? It's caving inside like this. Okay. Now I'll draw the non-reflecting surface right here. Okay. Now we're going to do the first term, that says the aperture. So it says the diameter of the reflecting surface of the spherical mirror. So what this means is these 2 points, say A and B. These are the ends of the spherical mirror. That is how big the spherical mirror is from here to here. So the aperture is basically the diameter of this. Diameter, we are not referring to any circle in the case of diameter here. By diameter, we just mean the distance between the two ends of a mirror, of a spherical mirror, is known as the aperture. So I have marked aperture as 1 here. So I am just going to write 1 here. So you know that this is the aperture. Now, second thing is the pole. Now, what is the pole? The pole, you know, in case of, like in the case of Earth, where the poles are. If this is the equator, the poles are at the tip, right? And at the center, exactly at the center of both the hemispheres. If this is the northern hemisphere, then the pole is right here. If this is the southern hemisphere of Earth, the pole is right here in the middle. The pole is not here or here, no. The pole is always in the middle. So similarly, the pole of a spherical mirror lies right here at the tip. Can you see? I've drawn a big circle here. The pole is it's a single point, but I've just drawn it just so that you're able to see it. The pole is not this big. The pole is like this. Just a dot. Can you see this? Just a dot like this. But just to tell you where it lies, I've drawn it this big. I've shaded it to be this big. Okay. This is number 2, which is the pole. Okay. I'm not writing it or it would get very messy. You can refer to the numbering here. The second is pole, which says the center of the reflecting surface of a spherical mirror is called the pole. So the definition you have to learn from your PPT and your books. I'm just explaining it to you so that you don't forget. Okay. Now pole, like the poles at the North Pole and South Pole in case of Earth, right here in the middle of the reflecting surface. Great. Now the center of curvature. So if you remember, as I told you in the last video and in the starting of this video, this spherical mirror is always cut out from a bigger sphere. Okay, the cricket ball that we were referring to. Okay, my sphere does not look like a sphere at all, but bear with me, you know this is a sphere. Okay, so this big sphere from which this mirror, I'm calling this mirror M1, this concave mirror M1 has been cut out, that sphere's center is the center of curvature. Every sphere has a center, right? Inside a cricket ball, there is some sphere somewhere inside, right? That is known as the center of curvature. So let's read in the PPT. The reflecting surface of a spherical mirror forms a part of a sphere. We know this, like this cricket ball that I've drawn, or any other ball that you like, football, basketball, whatever you like, right? It's a part of this big sphere. It's been basically, like, if you think about it like this, it's been like cut out from the sphere, like we have been doing. I just did it in the first slide in the PPT, and I did it in the last video as well, right? We cut it out from a big sphere. So that big sphere basically, that big sphere's center basically is the center of curvature. Okay, there we have our third point, the center of curvature. Okay, keep referring to the numbering here. Okay, I've just mentioned it here and I've written the numbers. Now we come to the radius of curvature. Again, we come back to the point that this mirror has actually been cut from a huge, or not so huge, just a sphere, right? So every sphere has a radius. Basically, every shape has a radius, a diameter, some dimension to it, right? So in the case of circle or a sphere, we always talk about radius or diameters, right? So here, the third thing, what did we mark here? Quickly, we mark the center of curvature, this big blob. I can make it a little smaller. This is the center of curvature. And what is the radius? The radius is the distance between the center and any point. Here I've drawn it to the pole. You can draw this line also. You can draw this line also. Any line that you want. Any radius of this whole sphere, be it this radius, be it this radius, wherever you want to draw the radius, this distance between the center of curvature and any point on this sphere is known as the radius of curvature, which is the fourth thing here. Okay, now let's read it. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part. Basically, it's just a complicated way to say that the sphere that we have used, from which we have cut that mirror, the radius of that sphere is the radius of curvature. Okay. Now moving on, the fifth point term is focal length. Now what is the focal length? This is going to be of a lot of importance. The focal length is basically the distance between the pole and the principal focus. Now pole we know, right here we've marked number 2, pole. But what is the principal focus? Right now I'll just define it in a very layman's way, but as we go forward in this video, we would understand what the principal focus is. Okay, so I am going to say that the principal focus is the midpoint of the radius. Okay, so I am going to say that the midpoint of the radius is known as the principal focus, but it is going to be of much more significance as we go forward. Okay, this is just a beginning definition for you. Okay, let's move on. Now, the center of curvature, as we just discussed, is the sphere that we are considering. It has a center, and this point is called the center of curvature of the spherical mirror. I don't need to do it again and again. This sphere that we are considering, even if this is the reflecting surface or the outer surface is the reflecting surface, doesn't matter. When this sphere's center is the center of curvature. Okay. Now this is the important point. The center of curvature is not a part of the mirror. Okay, this is the important thing. As you can see, we can cut out this mirror. We can cut out this mirror. We can cut out a mirror like this. This could be the mirror. And if we want this mirror, we can cut it out like this. So can you see that the center of curvature is actually not coming in the mirrors. It is outside of the mirror. It is not lying on the mirror. Like the pole, where does the pole lie? Right here on the mirror, right? Like that, center of curvature doesn't lie on the mirror. Center of curvature lies outside of the mirror. Okay, it lies outside the reflecting surface, as your PPT says. Now, the center of curvature of a concave mirror lies in front of it. However, it lies behind the mirror in case of a convex mirror. And why is that? Look, if we are considering a sphere like this, okay, and these are two spheres. One of these spheres I'm going to make a convex mirror out of. One of these spheres I'm going to make a concave mirror out of. So this sphere I'm saying I have to cut out a concave mirror. So which part should I shade as the non-reflecting surface? Should I shade the outer part as the non-reflecting surface, or should I shade the inner part? Think about it. Take a second. Yes, we are going to shade the inner part as the non-reflecting surface. Oh, sorry. So which part am I going to shade? Am I going to shade the outer part if I want a concave mirror, or am I going to shade the inner part? Think about it. Take a second. Yes, we are going to shade the outer part because we want a caving in mirror. We want our reflecting surface to be caving in like a cave. Okay, so here I am cutting out a concave mirror. So when I cut it out, it's going to look like this, right? It's caving in inside, it's going inside like it's been pushed in, so it's a concave mirror. Now, look at this. Where is the reflecting surface? The reflecting surface is this surface, right? And where does the center of curvature lie? Here, right? Now, it says that in the case of a concave mirror, it lies in front of it. So see, the reflecting surface is here, and right in front of the reflecting surface is the center of curvature. But now look at the second circle, sphere. If I have to cut out a convex mirror from it, where am I going to shade? Obviously, if I shaved outside for a concave, I'm going to shade inside. So my reflecting surface is going to be inside, right? Now, so I'm going to shade inside. So my non-reflecting surface is going to be inside. The reflecting surface is like bulging out, like when you get hit on the head. See, it's bulging out, the reflecting part, right? This is the reflecting part of the mirror. So it's bulging out like this. Now, the center of curvature, is it in front of the reflecting part or is it in front of the non-reflecting part? Look at this. Which part is in front of the curvature, center of curvature? It's the non-reflecting part, right? This is the reflecting part. Like this is where you'll have to stand if you want to see yourself in the convex mirror. But this part is the non-reflecting part. So that is why it says that in case of a convex mirror, it lies behind the mirror. It says behind, right? The center of curvature lies behind. Like this is the mirror. You can see, if I cut this mirror out here, this is the mirror, and the center of curvature, if I compare it to the above diagram, is somewhere here. So this is the front of the mirror and the center of curvature actually lies behind the mirror. Okay, let's move on. Now the principal axis and the principal focus. What is the principal axis? The principal axis is just the line that joins the pole and the center of curvature, or the line that passes through the pole and the center of curvature. That is, if I have a concave mirror, this is my pole, I told you, and suppose this was my sphere. Now, students, I'm just drawing this sphere right now. I'm not going to be drawing it every single time. I've drawn it a few times, so now you have to just imagine every time I say the sphere that the mirror is a part of, that this dotted line should immediately come into your mind. You should see that dotted line when you see a mirror. You should imagine that mirror which the that sphere that the spherical mirror is a part of. As soon as I say that the sphere that the mirror is a part of, you should imagine this dotted line. Okay, I will not be drawing it again and again. Now, this is the center of curvature. This is the pole. This line that passes through the center of curvature and the pole is known as the principal axis. Okay. Now, the principal focus, this is very important. How I am going to define the principal focus is a little different than how it is given here. So in case of a concave mirror, how do I define the principal axis? I define it as the point at which all rays coming from infinity converge. I'm going to explain this, don't worry, okay? In case of a convex mirror, the point at which all rays coming from infinity appear, this is very important, appear to diverge. Okay, appear to diverge and converge. These are the two important things. Now I'm going to give you a second. Write these two definitions down. This definition is for what is the principal focus. What is the principal focus in case of a concave mirror and in case of a convex mirror. Okay, take a second, write it down, because now I'm going to erase it so that I have space to show you through a diagram. Okay. Okay students, so I hope you have noted this down. Now I am going to remove this definition and I am going to draw a figure so that it is easier for you to understand. Okay, now we are going to see why I said why we define the principal focus of the concave and convex mirror like that. Okay, now let us consider a concave mirror first. I'm just going to have these two diagrams up here for you. This sphere where the outer surface is shaded is for which mirror? Is it concave or convex? It is concave, because if we cut out a mirror like this, the reflecting surface would be caving in, right? And this sphere which is shaded inside, in this, the reflecting surface is what? Bulging out like you've been hit on the head, and this is for the convex mirror. We can cut out a convex mirror. So I'm just drawing this here for your reference, okay? Now, when I said that in case of a concave mirror, the point at which all rays coming from infinity seem to converge. Converge, do you know what the meaning of converge is? Converge basically means meet. Okay, so all rays that are coming from infinity means the sun is at an infinite distance away from us. Okay, even though the distance of the sun from the earth can be measured, and it is measured, but because it is a huge distance, we assume that it is at infinity. Okay, like the light here in front of me is at say 3 meters from me. It is a measurable distance, but that is like thousands and thousands and thousands of kilometers. So we call it infinity. So how we depict rays coming from infinity, this is also something that you have to always remember. That, I'm so sorry, I'll just draw a straight line. This is the pole. Somewhere here, now immediately you have to link it to these two spheres that I have drawn. This is a concave mirror, caving inside. So which sphere? First sphere or second sphere? I've written convex both places. I'm so sorry. So which sphere? The first sphere or the second sphere? Is this mirror a part of? Concave. I've written there. I've already written concave and convex. But you should also be immediately thinking, okay, where is the reflecting surface? Is the reflecting surface caving in, or is the reflecting surface bulging out like you've been hit on the head? and immediately as soon as it's caving in, a concave mirror. As soon as it's like bulging out, it's a convex mirror. Okay, then as soon as you say okay, bulging out, so you should think if it's bulging out, that means the radius of center of curvature is behind the mirror. If it's caving in, the center of curvature is in front of the mirror, right here. Okay, I think that concept is clear to you now. So we said that the principal axis is passing through the center of curvature. Somewhere here is the center of curvature, and this line is the principal axis. Now what we have to always remember is that this is a little point that you always have to use. Rays coming from, I hope you know this is the symbol for infinity, okay? Rays coming from infinity are, this is the symbol for parallel to principal axis. Okay, so this is something that you always have to remember, that rays that are coming from infinity are parallel to the principal axis. So right here, we'll just consider two rays for simplicity. Wow, very straightly drawn. I'm so sorry. Please draw it well in your notebooks, okay? So here one ray is coming. Now, this is something that is very important, students. So now you remember that when we had done plane mirror, I had said that what is the normal to a mirror? Quickly think about it. A normal is a line that is at 90 degrees to the surface of the mirror, right? So now and a normal for a plane mirror is in the same direction, because a plane mirror is straight. If this is my plane mirror, if I draw a normal here, it is in this direction. If I draw a normal here, it is in this direction. If I draw a normal here, same direction. But as soon as my mirror becomes curved, now at this point, if I have to draw a normal, a line at 90 degree, it is like this. Okay, it's pointing somewhere up. But at this point, where would the perpendicular be? Where would the line perpendicular or at 90 degrees to it be? It would not be above. It would be right here in front. I would draw diagram so it's more clear to you. Okay. So say this is our spherical mirror. Okay. Forget convex and concave right now. I'm just focusing on the normal part. So look at this point. This point. For this point, what is the surface? The surface is this part. Just a small surface only we need, this part. Now, at this part, where would you draw a perpendicular? A line at 90 degree. Would it be this line? Would it be this line? Would it be this line? A line that is at 90 degrees to this surface. Come on, tell me 1, 2 or 3. Correct. It is 2. Because 2 is exactly at 90 degree. Now, I'm going to erase whatever we don't need right now. We don't need this. We don't need this. We just need this line at 90 degree. Now, if you look at this part, this point, somewhere near the pole, for this point, what would the surface be? A small part of the surface is somewhere like this, somewhat like this, right? Now, to this point, where would the perpendicular lie? Would it be like this? Is this a line at 90 degrees to this surface? Almost. Or is this the line, or is this the line? Correct. This middle line is the line at 90 degrees. So can you see the two perpendiculars to the surface at two different points point in the completely different direction? Whereas in the case of a plane mirror, at this point the surface 90 degrees is this. At this point a line at 90 degrees is this. At this point a line at 90 degrees is this. All in the same direction. I drew an E basically, right? But in the case of a spherical mirror, that is not what it is. It is actually different at different points. So that is something that you have to remember. So, and you remember this, the first law of reflection. What did it say? Think. The first law said that the angle of incidence is equal to the angle of reflection. Now, with all that information in our mind, let us, the first thing I told you is you draw a normal. If we have to see where the reflected ray would go, we said that angle of incidence has to be same as the angle of reflection. But right now, and what did we measure the angle of reflection and incidence from? we measured it from the normal, right? We always measure all the angles from the normal. But right now I don't have a normal here. So what do? I draw a normal. And I just told you that if you have to draw a normal at this point, you just take this small surface. You just imagine this small surface and imagine where a normal to this surface would lie. It would lie somewhere here, right? See, it is at 90 degree to this small surface of the mirror that I have considered. Okay, I am erasing this. Now, if this is the angle of incidence, I have to basically draw a line which has almost the same angle from this normal. I should have drawn the normal dotted. Okay, the normal is always dotted. That should have the same angle with the normal as the incident ray. So somewhere around here looks like the same angle, right? So this is your principal focus. Now if I draw another ray for you, this is another ray coming from infinity. Here also I draw the normal. Here this small surface, so the normal is somewhere here. Again I draw, this is, now this time this is our angle of incidence. This is our I. Okay, now if I draw almost at an equal angle, like I'm not taking precise angles, that's why it won't come exactly like that. But if you measure it and make it, it would pass through this point only. So both the reflected rays, this reflected ray and this reflected ray, it passed through the same point, which is the principal focus. Okay, this was in case of a concave mirror. Now if we take the case of convex mirror, it is a little more interesting. Let's see. So we'll draw convex mirror and we're simply going to use the laws of reflection that we know. Okay, and then we'll connect it to the line that I had written, that in case of a convex mirror, the principal axis is the point from where all rays coming from infinity appear to diverge. So it sounds like a complicated sentence, but once we draw this diagram, it would become clear to you. Then you will be able to form the sentence on your own. Okay, so this is the first ray from infinity that I am considering. Okay, now again, this small part, where would the normal lie? Somewhere around here. Now, first law of reflection, angle of incidence is equal to angle of reflection. So where does my reflected ray go? Somewhere around here. No, I made it a little bit far away. It's somewhere around here. Yes. So this is my angle of reflection. This is my reflected ray. Second ray, if I take like this, at this point, where does the normal lie? Somewhere around here. Okay. And the reflected ray would lie somewhere around here. Look, like this maybe. Okay, so I'm just taking rough measurements. If you draw it with a protractor, you will get a perfect diagram. Now, can you see that in the case of a concave mirror, right here, look here, the rays were reflecting and meeting at one point, right? But can you see these reflected rays meeting in case of a convex mirror? No, right? One ray is going in this direction and one ray is going downward. So there is no way that they are meeting in real life. But what if we back trace these rays? What if I just go here and trace this ray backwards with a dotted line? Dotted line always, because there is not actually any ray there. Okay, and this ray, if I take this as my reflected ray and I take this dotted line, see, it is supposed to converge, but because I have not taken proper measurements, it is not converging. When you draw it with a D, it will converge. Okay, so it's somewhere here and this goes and converges like this. Okay, so right now my lines aren't straight at all because I am drawing on this virtual board, so it is not exact measurements. But when you draw it on paper, you will see that when you take this angle of incidence equal to angle of reflection and everything, that when you trace these 2 points, like I had to do some manipulation, I had to take the line like this, like a curve. But when you do it with proper measurements, you would not have to do that. It would come like a perfect line and it would meet here. So now do you see? Now what does diverge mean? Converge means to meet. Diverge means going in different directions. So from this principal focus, this point, doesn't it look like these reflected rays are going outside? Look at this line going like this. This is the reflected ray. This dotted line going like this is the reflected ray. It seems that they are going outwards from that point, right? Even though we have back traced it, that is why we say they appear to diverge, because they are not actually diverging. They look diverging only when we have retraced and made them meet at that point. So we say appear to diverge, but in case of a concave mirror, they're actually converging in real life also. Okay, so that is what is means that these points, these rays coming from infinity appear to diverge from this principal focus that is behind the mirror. And principal focus is behind the mirror because look at this sphere. Where does the center of curvature lie? Behind the mirror, here. Where does the principal focus lie? Behind the mirror, here. Okay, moving on. Now aperture, again we have done this already, that the aperture is the distance between these 2 points in case of a convex mirror or in case of a concave mirror. Okay, so the reflecting surface of the spherical mirror is by and large spherical. The surface then has a circular outline, the diameter of this reflecting surface. So this diameter basically is the aperture. Okay, now we have just done this, a concave mirror whose reflecting surface is curved inwards, caving, is known as a concave mirror. And this ray diagram we just did. Okay, you can make it with 4 or 5 rays, it would look even more good. And this is just the ray diagram that I drew with just my hand, so it was not that precise, but you can see here how precisely your diagram will come if you take proper measurements and if you draw it with a scale and a protractor. Now, why does the paper burn when exposed to sunlight while using a concave mirror? Now, in case of a concave mirror, we saw that all these lines coming from infinity, they meet at one point, right? These lines, they all like meet here. Reflect, okay, they meet here, right? So think about at this point, think about if all the light from the sun was focused at just one point, how hot would that point be, right? That is exactly what happens. Like when you hold a concave mirror like this and you focus and you just take a piece of paper and you take a concave mirror and you take the mirror close to the paper, take it away from the paper, take it close. So you'll see that at one point, at one position, the sun's rays would appear absolutely like a dot. Like if you take the concave mirror very far, the sun would look very big. So it's not focused at one point, but at a specific length. And what is that length? The focal length. Because where do these rays come and converge? At the focus. So at the focal length, when you've held the concave mirror exactly at the focal length from the paper, all the rays from the sun converge and focus at one point. So that point becomes so hot that the paper actually starts to burn. Okay, this is a very interesting exercise that all of you should try at your home. Now the conclusion is the light from the sun is converged at one point and a sharp bright spot is seen in the mirror. This is the focus of the concave mirror, and the heat produced due to the concentration of sunlight ignites the paper. Okay, let's move on. Now this is a convex mirror. We have seen in case of a convex mirror, bulging out surface is a convex mirror. It's curved outwards like you've been hit on the head. Okay. And in case of a convex mirror, like my lines did not seem to come perfectly from this focus, but they have drawn it exact measurements with exact measurements. So see how beautifully it comes out. Okay. So you have to draw it on your own with a protractor and scale. Now, this is a very important and simple relation that you have to remember between the radius of curvature and the focus. So say that this is the sphere and this is the radius of curvature of that sphere. So the focus lies exactly at the midpoint. So if you say that this is the focal length of a concave mirror, say 2 centimeters, then exactly 2 centimeters from here, that is double of the focal length, at 4 centimeter is the radius of curvature. This whole is the radius of curvature. Okay, that is what you have to remember. Now students, in this video, we talked about what spherical mirrors are. We looked at some ray diagrams and we saw what some important terms like aperture, center of curvature, radius of curvature, principal focus are. And we drew some very important ray diagram related to converging and diverging of rays. Okay, practice all of these diagrams, make them yourself and solve some questions if you can. Okay, I hope you enjoyed this lecture. Thank you and take care.